Hello and welcome students. How are you? How you are keeping yourself? In this chapter, chemical bonding and structure of molecules, we discussed so many different theories in the last few classes. Like we discussed about the ionic bond, we discussed about the covalent bond, we discussed about the structure of the covalent molecule. But let me tell you one thing. There are few molecules in which valence bond theory is not sufficient enough to explain the properties. In order to explain the bonding in them, we introduced the new concept, that is molecular orbital theory, MOT, molecular orbital theory. In today's session, I'll tell you about the molecular orbital theory. So come, let's study the features of molecular orbital theory. So in this today's session, we will discuss about the molecular orbital theory, MOT. In short, it is called as MOT, which is put forwarded by the LCAO method. LCAO stands for linear combination of atomic orbitals. Then we will tell you about type of the molecular orbitals, relative order of the energies of the molecular orbitals, how to calculate the bond order, and finally we will discuss molecular orbital diagrams in this session. So here we go. Molecular orbital theory, which is MOT, it was developed by Hund and Mulliken 1932. Into 1932, they developed the theory, molecular orbital theory. Do you know what is the need of this theory? Basically, at that time, VBT was in trend. So what was the need of this theory? According to this theory, atomic orbitals of the bonded atom, they mutually overlap to form new orbitals called as molecular orbital. This is the biggest difference between this molecular orbital theory and the valence bond theory. In the valence bond theory, we just say that in the bond formation, there is a role of outer shell only. Means the electrons of valence shell only participate in bond formation. But here in the MOT, all the orbitals participate mutually to form the molecular orbitals. It is very much different than the VBT. VBT was failed to explain magnetic behavior of some molecules like oxygen. So that was the biggest success of this MOT. It was, capable enough to explain the magnetic behavior of oxygen molecule. So these are the features of MOT, molecular orbitals. Those orbitals which belongs to molecule. The orbital which belongs to atom is called as atomic orbital, and the orbital which belongs to molecule is called as molecular orbital. So they are the regions in the space where electrons are most likely to be found. The wave functions of an electron in a molecule is called as molecular orbital. Molecular orbitals are formed by the combination of the atomic orbitals in the linear fashion. But it is not like that any atomic orbital overlap. The atomic orbitals of the comparable energies, only those atomic orbital for which energy is comparable and they have proper symmetry, means orientation, only they combine linearly and form MO. Like the hybridization, in the hybridization, number of hybrid orbitals formed equal to the number of orbitals combined. Same in this, the number of atomic orbital combining is equal to the number of molecular orbitals formed. So if two atomic orbitals combine, if two AO combine, two MO will form. If 4, then 4 MO will form. The atomic orbital AO, which belongs to each atom, they combine to form two molecular orbitals. Now these molecular orbitals which belongs to molecule, they itself are of two types: bonding molecular orbital and anti-bonding Bonding molecular orbitals are those which are lower in energy and higher in stability. So the electron which is present in BMO, they stabilize molecule, and the electrons which are not present in BMO, they destabilize molecule. So ABMO, they have higher energy and lower stability. Energy of the ABMO, antibonding molecular orbital, is higher, and as a result their stability is low. See, this one is AO, this one is also AO. These are the orbitals belongs to atom. When they combine, they form MO. Both of them is MO. Out of them, this one is BMO, bonding MO, and this one is anti-bonding MO. In short, I will call it ABMO, and this will be called as BMO. You see, this is the order of energy. So BMO is lower in energy and ABMO is higher in energy. A molecular orbital can accommodate maximum of 2 electrons like any other simple orbital of s, p, d or f. MO are polycentric. What do you mean by polycentric? Electron cloud is under the influence of more than one nuclei. In the MO, electron cloud is not controlled by the single nuclei, whereas AO are monocentric. AO belongs to the atom. So when they belongs to the atom, electron clouds are associated with the single nucleus, and the shape of MO depends upon the shape of AO. What kind of AO combine, and depending upon the type of AO, shape of MO is determined. In the filling of MO, 𝕆 principle is applied. You know 𝕆 principle? You must have studied the 𝕆 principle in the class 11th. Atomic structure. This 𝕆 principle is basically combination of Pauli's exclusion principle and Hund's rule, and also N+L rule. So MO follow all of them. Now we will discuss about the LCAO method. Like I said, LCAO method is the linear combination of atomic orbitals. What happens in the linear combination? In this method, the MO are approximated by combining linearly atomic orbitals. What I said? That atomic orbitals linearly combine. They combine linearly and then they form molecular orbitals, and they form molecule. In atomic orbital, it is considered as the electron wave. Orbitals are always the function of electron wave, and when wave is there, there is a crest and trough. In the crest, positive sign is there, in the trough, negative sign is there, or vice versa. So the wave goes as plus and minus, positive wave function and negative wave function. So it can be expressed in terms of the wave function psi. This is the Greek letter psi, psi, and it is expressed in terms of wave function. When the crest of the one wave overlap the crest of another wave, means crest overlap with the another crest, an attractive molecular orbital of low energy means BMO, is formed. So we can summarize that BMO are formed via in phase overlapping, when there is a no phase difference, same wave function, same phase, and when the crest of one wave overlaps the trough of another wave, a repulsive molecular orbital of high energy is formed, called as anti-bonding molecular orbital, ABMO. It is called as ABMO, anti-bonding molecular orbital, ABMO. Students, it is ABMO. Now you consider the formation of H2 molecule. Now we shall discuss how this hydrogen molecule is formed. See, in the formation of hydrogen molecule, let psi A and psi B, they represent the wave function of the atomic orbital AO of the two hydrogen atom A and B. when hydrogen forms, there will be one hydrogen atom and there will be another hydrogen atom. Let us consider this one is A and this one is B. Wave function of this one is psi A and wave function of this one will be psi B. So how these wave functions they combine with each other? When they combine linearly, this combination may be in phase or out phase, in the same phase or in the different phase, crest with a crest and or crest with a trough. So the wave functions undergo linear combination to produce molecular wave functions, which represents 𝕝. So this 𝕝 is either formed by the combination of the wave function or the subtraction of the wave function, depending upon the type of 𝕝, whether it is a BMO or it is a ABMO, whether it is of low energy or it is of high energy. So depending upon this, there is a formation of wave function of 𝕝. Now we shall consider two cases. Case number 1, when the two waves are in phase. In phase mean same phase, where phase difference is 0. In case when the phase difference is 0, they are combined in the in phase combination, they are added and the amplitude of the waves are also added, and because of the result, amplitude of the new wave, which is psi, is sum of the wave function of A and wave function of B, which is likely to be more than any individual wave function value of A and B. So here this bigger wave function means bigger probability of finding electron is there in the in phase combination. Case 2, when there is a two waves, they are out of phase. Out of phase means opposite phase combination. In the opposite phase combination, wave function of the resulting wave is equal to the difference of the wave function of A and B. In this case, they try to cancel out each other. In the amplitude, the resultant wave has definitely lower amplitude than any of the two waves, A and B. In case of in phase, the amplitude was greater than A or B, but now it is lesser than A and B because of the difference of the wave function between A and B. Electron density also reduces in this case. Now, furthermore, addition of the AO. So whenever or whichever AO combine, they give either BMO or they gives ABMO. Whether they produce bonding molecular orbital or they produce anti-bonding molecular orbitals. Either they produce BMO or they produce ABMO. If they produce BMO, wave function will be like this. If they produce ABMO, anti-bonding, wave function will be like this. So wave function of MO is sum of the wave function of A and B, and wave function of anti-bonding, which is most of the time represented by the star sign. This sign, this star is the representation of anti-bonding. Bonding molecular orbitals. A constructive combination in phase of two atomic orbital leads to the formation of bonding molecular orbital, my dear students, BMO. It leads to the formation of BMO. It is low in energy and high in the stability, and also high electron density between the two nucleus. Because energy decreases, density of electron between the two nucleus increases in case of bonding molecular orbital. When electron density increases, students, probability of finding electron also increases. So if you square the sum of the wave function, like I said, psi BMO is equals to psi A plus psi B. If you square all the quantities, then it will be psi B square is psi 1 square plus psi 2 square plus 2 psi 1 psi 2, means probability of finding electron in BMO is equal to the sum of probability of finding electron in 1 and 2 separately, right? And the value is still more. Finally, I can conclude this like probability of finding electron in BMO is 2 psi A psi B is 2 psi 1 psi 2 or psi A psi B more than the sum of probability of finding electron probability density than in A and B. So in total, probability of finding electron in BMO is greater. Here is the picture where you see this is the wave function of A and B for the individual atom, and this is the wave function for BMO, and this is the wave function represents the charge density. So this psi BMO square is psi A square plus psi B square plus 2 psi A psi B. It is 2 psi A psi B more than the sum of individual. So the charge density psi B square is greater than the sum of the charge density of two isolated atom A and B by the amount of 2 psi A psi B. Alright, it is greater than sum of both of them by 2 psi A psi B. Exactly opposite happens with the ABMO. ABMO forms out of phase combination of 2 AO when the 2 AO combine with each other and they form out of the phase combination. Then there is the production of anti-bonding molecular orbital, ABMO. It is a repulsive orbital of high energy and has zero electron density between two nuclei. Means zero electron density means some nodes will be there between the nucleus. Wherever probability of finding electron is zero, particularly that space is called as node. There is a formation of node between the nucleus of ABMO. What about the probability of finding electron? We know that in ABMO psi A is different psi B. So now we do the square, and after square what we get it, psi A square gives equal to psi A1 psi A square plus psi 2 square minus 2 psi A psi 1. Now it states just exactly opposite of the BMO. If this is the wave function of A and B, they are combining with each other in the opposite phase, out of the phase, there will be a formation of anti-bonding molecular orbital, ABMO, and the charge density psi A square is less than, now it is not more, it is less than the sum of charge density of the two isolated atom A and B by the amount same, 2 psi A psi B. So in the BMO, probability of finding electron is 2 psi A psi B less than the sum of probability of finding electron in A and B individually. Now how do we form the atomic orbital? Moreover, how do we combine the atomic orbital? There are some conditions. The combining AO must have the same energy or nearly the same energy. There should not be very much difference, which means one s orbital can combine with one s only, not with a 2s. If you will try to form any formation of MO between 1s and 2s, this will simply fails. No molecular orbital can be formed by the combination of 1s and 2s, as they have difference in energy, very much difference. Number second condition is combining AO must have the same symmetry about the molecular axis. They should be on the same symmetrical panel. Means if it is 2px, another should also be 2px. If it is 2pz, it should also be 2pz. There is no MO formation between 2px and 2py. No combination will take place. No MO will form. So 2pz orbital can combine along with the z-axis only with the another 2pz, not with the 2px, not with the 2py, and vice versa. 2py will not combine with any other 2px. 2py will combine with the 2py only. X will combine with the x only. A pz orbital can also combine with the s. Now if there is a combination of p and s, it will be pz and s. It is very important, students, please remember px and py, these orbitals does not combine with the s orbital. since if that happens, if that is believed to happen, then this positive overlap is cancelled by the plus minus overlap. So this is not gonna happen. All right, like it is explained in the picture. The third condition is combining AO must overlap to the maximum extent. When AO will combine, they will combine to the maximum extent. Why? Because greater the extent of overlap, greater will be the electron density between the nuclei of a molecular orbital and stable will be the bond. So this happens just in order to gain stability, nothing more. Now we shall discuss about the energy diagram. This is the energy diagram of molecular orbitals. This 2pz, when it combines with the another 2pz, there is a formation of one BMO, another ABMO. While we write these atomic orbitals in our copy, we form square boxes. But the real shape of these square boxes are look like this. This is BMO. This is also ABMO. You see this black line, it is nodal plane, a place of zero electron density. This is a nodal plane, plane of the zero electron density. These are the energy level diagrams in which 1s is combining with another 1s, which leads to the formation of sigma 1s and sigma star 1s. This one is BMO, this one is ABMO. In total, whether it is BMO or ABMO, they are in total MO. And this sigma star 1s, this is the real shape. And this sigma 1s, this is the real shape of sigma 1s. This is how it actually looks like, and this is how we draw it on paper. Huge difference between them. Then type of the molecular orbitals. There are two basic type of the molecular orbitals. One is sigma, another is pi. Both are MO, sigma MO or the pi MO. What is sigma MO? It is the molecular orbital formed from the overlap of two s orbital or head-to-head overlap of s and p, which will give rise to the sigma molecular orbital. Again, they can be of two types. Sigma molecular orbital can be of two types: sigma bonding and sigma anti-bonding. So sigma BMO and sigma ABMO. Please have a look. These are the shapes. When s orbital combine with the pz, they overlap in this manner and they form this one. This is MO. When p and p combine in the linear fashion, same axis, then there is a formation of this orbital called as sigma pz, because it forms sigma bond. The positive and negative sign used here represents the sign of wave function. Whenever wave travels, it always travels plus minus and goes on. Similarly, when s orbital linearly combined with pz orbital, but in the out phase combination, there is a formation of ABMO, and the shape of ABMO is like this. Nodal plane is there. But when pz and pz they combine in the destructive manner, out phase, there is a formation of again ABMO, which look like this. So this is the real shape of sigma 2pz and sigma star pz, sigma star spz. Another one are the pi molecular orbital. Pi molecular orbitals are those which are formed by the sidewise or the lateral overlapping of p. You know, lateral side by side overlapping. It forms the pi bond. It is also two type: pi BMO and pi ABMO. BMO when in phase, ABMO when out phase. This is how it goes. When plus combines with the plus, the sigma bonding molecular orbitals are formed BMO, because they combine in the same phase. And this is the result of the pi x, pi px or pi py, whichever. Alright. And this is the formation of anti-bonding, pi star px or the pi star py. You see, when anti-bonding orbitals are formed, positive wave function combined with a negative one, and the negative wave function combined with a positive one. This forms to the anti-bonding orbitals. Now here are a few differences between sigma and pi molecular orbitals. sigma molecular orbitals formed by the head-on overlap of atomic orbital, head to head on the internuclear axis, while pi is formed by the sideways overlap of the atomic orbital, and it is perpendicular to the internuclear axis. Alright, this happens over the internuclear axis, and this happens perpendicular to the internuclear axis. The overlapping of orbital is maximum in case of sigma bond because sigma is strong. Here overlapping is much less than what? Much less than sigma. In this, electron cloud is symmetric in the sigma bond, but in pi bond electron cloud is not symmetric because nodes are there in between them, and it results in the formation of stronger bonds as they have low energy, and these result in the formation of weaker bonds as they are higher in energy. This was about the molecular orbital theory and their features, and about the sigma and pi bonded BMO and ABMO. Now in the coming classes we shall tell you about the how to form the molecular orbital diagrams, how to find out the bond order, and also order of stability. This we shall see in the coming lectures. I hope you liked today's class. Please keep coming and keep studying. Good luck to you.